Hi, everybody. Can you hear me?
Yeah, I can hear you.
All right, thank you. Sorry about the delay there. I was having a technical issue trying to log in here. I don't know what the problem was. They gave me a new laptop. I think that has something to do with it. So I'm really sorry about that. All right, let me see if I can get this sharing sorted out here. Okay, all right. Let's have a look. Let's try this one. Okay. So we're looking at module 9 today. Is that correct? I believe so. All right, can you all see my screen here? I've got 3 different monitors going here and it's kind of crazy. Yes?
Yes.
Thank you.
Yes.
All right, so we're going to, we'll focus first of all on just a very short modified kind of flow chart that I like to use for stoichiometry. Let's see. All right. Okay. Let me see if I can, I'm going to have to change the share here, I think. Change it to that one. All right. I'll get this sorted out. All right, can you see my, hopefully you can see the 2 things here, the paint and the browser. Yes?
Yes, I can
Good.
see both.
Okay, thank you. Great. Okay. So when we're doing these problems, I like to use this modified flowchart here, QA, mole A, mole B, and then QB. And then I like to use dimensional analysis to solve these. The things we can always start with are grams or liters of gas at STP. And we'll pretty much just limit it to those 2, but you could use molecules and other things as well. And the things we can end with would be grams and again, liters of gas at STP. Okay. So that's what's going to form the basis of what we're doing here. So this is a fairly more complicated flow chart here, but I think it's a bit easier just to use this little modified one to, it does the same thing. It's just a little bit easier to remember and a little bit easier to go with. So let's say we're starting with how many moles of HNO3 we are required to form 6.5 moles of H2O. And in all of these kinds of problems, we're given a reaction because the whole point of stoichiometry is to be able to use a chemical reaction in order to figure out how much we're getting of something or how much we're using of something. And generally, it's pretty easy to tell what we're starting with because it'll have a number in front of it. Like this one here has 6.5 moles of water. So I know that's where we're starting. And with these, it's really important not just to include the unit, but also to include the compound as well, because we're always working with more than one compound from a reaction. And if you look closely at the flow chart here, we're starting out with something moles. And in the problem, we're going to moles of something. So I know that that's going to be a 1-step process. I know that moles of water will be on the bottom. And I know that moles of HNO3 are going to be on the top. The relationship between moles of water and moles of HNO3 are going to always be from the reaction. So you can see it's going to be 4 moles of water and 8 moles of HNO3. So that's how we know that that would be 13 moles of HNO3. All right, does anybody have any questions so far? So that's a fairly easy one to start with. What about something a tad more difficult? How many grams of S would be formed if 4.25 moles of HNO3 were consumed? Don't worry about words like formed and consumed. Those are kind of red herring words, really. They don't really play any part in actually solving the problem. The only thing that matters is what you're starting with and what you're finishing with, and just leave it at that. Oops. So select that. Okay. So we're going to be starting with 4.25 moles of HNO3. And we're going to be finishing with grams of sulfur. Now, in this instance, if we're looking at our flow chart, we're starting here at moles and then going to moles of A, going to moles of B, and then going to grams of B. So we know we're going to need 2 steps here to make this work. So I know I need two things in a line here. So moles of HNO3 go on the bottom to make that cancel. Now, since I want moles of water next, moles of S next, because I know that it goes from moles of HNO3 to moles of sulfur. And then the last thing I do is I need grams of sulfur, and I know moles of sulfur goes on the bottom to cancel the moles of sulfur on the top in the previous part. Now, the relationship here, according to the reaction, let's see if we can get the reaction back here. There we go. It looks like it's 3 moles of sulfur and 8 moles of HNO3. And the relationship between grams of sulfur and moles of sulfur is going to be the molecular weight of sulfur, which I've got down here is 32.06 grams of sulfur and 1 mole of sulfur. And then that's how I'm going to get my answer. Now, the answer is going to end up having 3 significant figures. And you see it'd be 51.1 grams of sulfur. And the sig figs will be determined by what we start with. So 3 in the beginning and 3 at the end. Does anybody have any questions? Anybody have any questions? All right. Everybody's fine with that, huh? All right. Let's we'll go on something a little bit more difficult then, since nobody had any questions about that. All right, what if we're going from grams to grams? Now, per the flow chart, you can see if we're starting out with grams, we have to go to moles, and then we have to go to moles, and then we have to go to grams. So grams of A goes to moles of A, goes to moles of B, goes to grams of B. A is always what we're starting with, B is always what we're finishing with. So that makes it fairly easy. We start out here with 20.25 grams, and that's going to be of Bi2S3. Then I know I'm going to need to do 3 steps here to get to where I need to be. So I know that down the bottom here, that's going to be grams of Bi2S3 to cancel. Now, the cool thing about this flowchart is that as we go through the flowchart, whatever's on the flowchart will always be along the top here of our working. So I know that along the top, we got 22.25 3.25 grams of Bi2S3. Then we're going to have moles of Bi2S3. Then it'll be moles of S, and then it will be grams of S. So it'll just mimic exactly what we're seeing in the flow chart. So that makes it fairly easy from there. Moles of Bi2S3, if we just do it that way. And you notice I'm not putting any numbers yet. I'm just putting in units because I love dimensional analysis. And then next we're going to do moles of sulfur, and then moles of Bi2S3 go on the bottom. And then grams of sulfur goes on top, and then moles of sulfur goes on the bottom. So looking at the relationship here, 1 mole of Bi2S3 is equal to the molecular weight, which is 514.14 grams. And then the relationship between moles of sulfur and moles of Bi2S3, we get that from the equation. So 3 moles of sulfur and 1 mole of Bi2S3. And then the last thing here is the molecular weight of sulfur, 32.06 grams and 1 mole. Now, a very common mistake that I see here is that sometimes people will put 3 moles of sulfur on the bottom here. And the reason they're doing that is because they see the 3 over here in the reaction. And they think, oh, yeah, so it's going to have to be a 3 on the bottom. No, it's not the numbers that have to cancel. It's the units that have to cancel here. The other thing is that 32.06 grams of sulfur is equal to 1 mole. So anytime you've got something over something in the dimensional analysis, it's always going to be the situation where they equal each other. And 32.06 grams doesn't equal 3 moles, it equals 1 mole. So the answer to that comes out to be 3.788 grams of sulfur. So again, you'll notice the significant figures, which are going to be determined by what we start with at the beginning of the problem. So we end up with 4 at the end. Does anybody have any questions? I can't believe everybody's fine with that, seriously.
I mean, it's somewhat straightforward.
Okay, do you have a question though?
No, not at the moment. We'll see when we get further down the line.
Okay. The hardest part of this is going to be the percent yields. That's what people tend to really get upset about. Now I like this one here, because we're switching between liters and grams. So this one's kind of a cool one to do. But we're starting out here with 205 grams of sulfur. Roland, you might want to mute, please. Thanks.
I don't think that was me.
Oh, you don't think it was you? Okay, so somebody needs to mute. Thanks. So again, look at the top, and that'll give you some guidance about where you need to go. So we know we need moles of sulfur. That'll be first. And again, we need 4 steps because we're going from grams to liters. So grams of sulfur goes on the bottom here to cancel that on the previous part. The next is moles of, well, what are we looking for? We're looking for moles of NO. And then moles of sulfur goes on the bottom here to cancel. And then we have liters of NO at the end, and then moles of NO at the end. All right, I'm going to stop there. Make sure everybody understands exactly what I'm doing here. Does anybody have any questions?
Why are you going from grams to moles? And then how do you go from a mole of sulfur to a mole of NO?
Well, that's from the reaction. You see, that's the relationship from the reaction here. So you can see the relationship is that, what are we doing? Moles of S. So it's 3 moles of S and 2 moles of NO. All right, that's the relationship between them. That's how we're going between them. Are you okay with why we need 4 steps for that, David?
Couldn't you just go from grams of? Actually, no. It makes sense. It makes sense. Never mind.
Okay. Well, just following the flow chart, there's no choice.
Yeah. Well.
There's no choice but to go from grams to moles, and then back to liters here.
Yeah, that makes sense.
Okay. So the relationship between moles of sulfur and grams of sulfur, 1 mole of sulfur, 32.06 grams of sulfur. And then the relationship between moles of NO and moles of S, we've got 2 moles of NO and 3 moles of S from the reaction. And then the relationship between liters and moles, 22.414 liters and 1 mole. So that comes out to be sorry, I've got to get this sorted here. It comes out to be 95.5 liters of NO. Again, three sig figs, and then 3 sig figs at the end. Now, let me give you a calculator tip here to help you out. When I'm doing these, a lot of people like to, I don't know, they like to do it in order. I prefer just to do it multiply everything across the top and divide everything on the bottom. So this works pretty well. So you go 205 times, and then 2 times 22.414. So everything across the top gets multiplied. And then anything on the bottom gets divided. So divided by 32.06 and divided by 3. And that'll give you your answer as well. So that's a whole lot shorter than what a lot of people will try and do. Notice I ignored the ones, obviously, but that's the best way of sticking it in your calculator. Does anybody have any questions?
So it's pretty common for all of these for the actual equation to already be balanced.
Oh, it will always be balanced.
Okay.
I'm promising you that. For module 9, yeah, because this is not about balancing. This is about stoichiometry. So every equation you're given to help you out will always be balanced from the beginning.
Okay, thank you.
So we'll always have a ratio to reference off of.
Oh, straight away, you won't have to figure out anything. I mean, you won't have to do any balancing for the reaction first. I mean, that's kind of cruel. I could do that, but that's not what we did balancing back in module 6, so I don't want to rehash that again. I mean, module 9 is difficult enough without throwing balancing back at you again. All right, does anybody have any questions? Okay. All right, let's look at percent yield. This is where things start to get a little bit more difficult. All right, let's talk about what a percent yield is to begin with. Now, percent yield is always a percent yield always has a reactant and a product in it, always. And what we know is that the reactants are always on the left side of the arrow, and the products are always on the right side of the arrow. And sometimes in chemistry, we have names for things that don't make a whole lot of sense, but in this case, reactants and products do make a lot of sense. Reactants are the things that are reacting, and products are the things that we're getting. So I think that makes a whole lot of sense. And if you look at this problem here, it says, what is the percent yield of sulfur if 100.0 grams of Bi2S3 is reacted to form 10.0 grams of sulfur? Now, I know a lot of people don't really like word problems, and that looks like a lot of words. And, what do you need to do with all that? Well, just break it down, because you're always asked for the percent yield of a product. You're always asked for percent of the product. I really want you to, I don't want you to just hear those words. I want you to feel them right in here, right in your heart. Because if you can understand that you're always looking for a product, then you know where you always need to start. And that's not at the product. You're always starting at the reactant. So for something like this, what is the percent yield of sulfur if 100.0 grams of Bi2S3 is reacted? So it even says is reacted. So you know that that's a reactant. But you can see it up here in the reaction as well. It's on the reactant side. Sulfur's on the product side. So what is a percent yield? Well, the thing is, in chemistry, when we do reactions, usually we don't get back everything we're expecting to get. So what we do is we try and figure out exactly how much product we're expecting to get, and we compare it against what we actually got. So when you're looking at a percent, it's always, I like to use pizza as an example. That's 100% of a pizza. And if somebody eats some, let's say that would be about 75% of a pizza. So it's always what you have divided by the whole. And if you've already taken some out, then what's left, and divide that by the whole, that gives you the percentage left over. It's the same thing if we're talking about the amount of product we're getting. So we get an amount of product we're supposed to get, which I call a theoretical yield. And then I divide that by what we actually got, which is called the actual yield. And that's also in the problem as well. See, what makes these problems confusing is that there's two things with numbers in front of them, so it's difficult at times to know where to start. But the thing is, you can't start with the product because that's what you want. You got to start with the reactant. So it's always the other thing that you're starting with, and there's always a reactant, there's always a product. All right, does anybody have any questions?
So basically you're saying that, like, in theory, you can get 100% of the reaction, but say if you only got like 80% of the reaction, then you just do 100% over 80.
Yeah, but it's not going to be quite that easy because but you're right. Yes.
Okay,
Well, it's 80 over 100. It's 80 over 100.
Oh, it's the other way around.
Yeah,
So it's actual yield over theoretical yield.
Yeah, that's right. It's always part divided by whole. That's what a percentage always is. Part divided by whole.
Gotcha.
Like if I wanted to find out the percentage of females who were logged in here, I'd count up the number of females and then divide that by everybody, the whole, right?
Right.
So it's no difference to that.
I just wanted to simplify a little bit just so we got the big, I got the big message out.
Are you okay with that?
Yeah, I'm okay with that.
Okay, good. So we're starting out with 100.0 grams. Of Bi2S3. And then we know we need 4 steps here to get to, well, what are we looking for? According to the problem, we know that we get 10.0 grams of sulfur, but we need to figure out, well, how many grams of sulfur are we really going to get? Or were we expecting to get? So I know that grams of sulfur is going to be at the end here. And not 10 grams, but grams of sulfur, because we need to figure out how many grams we were supposed to get. So we go grams of Bi2S3 on the bottom. We got moles of Bi2S3 on top. We'll have moles of sulfur on the next part and moles of Bi2S3 on the bottom to cancel that. And then moles of sulfur on the bottom to cancel the moles of sulfur from the top. Then I put in my relationships here. I think it's 514.41 or 14. And then the relationship between moles of sulfur and Bi2S3 be 3 moles of sulfur, 1 mole of Bi2S3, and then the molecular weight, 32.06 grams of sulfur, 1 mole of sulfur. When all said and done, we come out with 18.71 grams of sulfur. Now, what does that number actually represent? Well, it represents how many grams of sulfur we should have gotten from the reaction. If we'd started out with 100.0 grams of Bi2S3, we theoretically should end up with 18.71 grams of sulfur. We actually don't get 18.71 grams of sulfur. We're going to get here 10.0 grams of sulfur. We know that from the problem. So the percent yield is going to be 10.0 grams sulfur divided by 18.71 grams of sulfur. So it's a little bit more than half, which would be, in this case, 53.4%. So we got about half of what we expected to get from that reaction. So these percent yield problems always have two parts to them. The first thing you need to do is figure out how much you should have gotten, or the theoretical yield. And to do that, you're going to always start with a reactant and go towards a product. Now, what unit do you put on the product? Now, that's another wrinkle here. Because in order to compare apples to apples at the end here, we need to make sure that the unit that we're getting at the end, the 10.0 grams of sulfur, is going to match the theoretical yield. So that means we need grams of sulfur for our theoretical yield as well. So whatever unit you have for the product in the problem is going to be the same unit as you're going to have at the end, the theoretical yield. Does anybody have any questions? I can't believe everybody's okay with that. All right. All right. Fair enough. Let's look at limiting reagent then. Now, the theory behind limiting reagent, I go into that here in the soft chalk. It's like if you have 2 slices of bread and a slice of cheese, you can make a cheese sandwich. And we know that if we had 2 slices of bread and 1 slice of cheese, we know we could make 1 cheese sandwich. Likewise, if we had 4 slices of bread and 2 slices of cheese, we could have 2 cheese sandwiches, and et cetera, et cetera. But if we vary that a bit, because this is our reaction here, it's effectively, whoops. What happened there? All right. All right. So if we had 2 slices of bread and 1 cheese, that's our reaction. And gives 1 cheese sandwich. Now, if you had, say, 8 slices of bread and 2 slices of cheese, how many cheese sandwiches could you make?
2.
2, right, because you only got that much cheese, right? So 2 cheese sandwiches. If we did that, we'd have 4 slices of bread left over. Likewise, if I had, let's say, 10 slices of bread and 7 slices of cheese, the most I could make would be 5 cheese sandwiches. And there would be 2 slices of cheese left over. So what we're talking about there is limiting reagent. In the top one of 8 bread and 2 cheese, cheese is limiting. In the bottom one, it's going to be bread that's limiting. But look at the mole ratio as well, or the bread ratio. You've got 2 to 1. So we need two bread for every 5 cheese. Sorry, we need 2 bread for every 1 cheese sandwich that we're making. We get that from the reaction up here. So you can see the ratio at the end comes out to be 10 gives 5. 10 bread gives 5 cheese sandwiches. So we need to take a similar approach here when we're dealing with limiting reagent problems, believe it or not. Does anybody have any questions so far? All right, so let's take a look at what we would do with something like this. Well, what we need to do is figure out how many moles we have of each. And then, let's go back to the problem here. We're starting out with 100.0 grams of Bi2S3, and we're reacting it with 99.00 grams of HNO3. So this is another thing you'll notice about limiting reagent problems. You're only ever given reactants, ever. That's it. You're only ever given reactants. So you're comparing them. You're saying, well, which one gets used up first? And the idea is you need to take into account 2 things: how many moles you have of each, and also what the mole ratio is of one to the, how many moles there are of each in the reaction, how many moles you need in order to get this going. So we need 1 mole of Bi2S3 to react with 8 moles of HNO3. So we need to take that into account as well. But so to do this, we start out with 100.0 grams of Bi2S3. We know grams of Bi2S3 goes on the bottom. We know moles of Bi2S3 goes on the top. And then we divide by the number of moles of Bi2S3 from the reaction. But let's do this for part first. 1 mole of Bi2S3, 514.14 grams. Then 1 over 1 mole of Bi2S3. Now, often people are wondering, well, what's this 1 here? What's the unit next to that? Well, there isn't one. It's just a way to divide by something. So if you want to divide by 2, you know you can multiply by 1 over 2. If I want to divide by 1 mole of Bi2S3, then I do times 1 over 1 mole of Bi2S3. This comes out with a number that I call a mole ratio. And this mole ratio here comes out to be 0.1945. Now this doesn't have a unit because everything cancels. And then I've got 99.00 grams of HNO3. I want to do the same thing with that. So moles of HNO3 goes on top. Grams of HNO3 goes on the bottom. Then it's 1 over 8 moles of HNO3. Now the 8, of course, comes from the reaction. And it's right there. So it's like with the bread and the cheese where we had two breads. We had to take the 2 breads into account. Here we're taking the 8 moles of HNO3 into account. The relationship between moles and grams for the HNO3, 63.015 grams of HNO3 to 1 mole of HNO3. This comes out to be a mole ratio as well, and that one's 0.1963. Now, since this one's smaller, then I know that Bi2S3 is going to be limiting. So whichever mole ratio is smallest, that's the one that is going to be limiting reagent. All right, so just summarizing what I just said here. In a limiting reagent problem, you're always given just reactants. That's the first thing. We need to take account of two things when we're doing this, two things. The first thing is how many moles of each we have, and then how many moles there are in the actual reaction. In order to do that, we make a mole ratio by doing a division. And that division is the same as doing times 1 over something. And then comparing the two mole ratios we get at the end. Does anybody have any questions? Does anybody have any-
Why do you do 1 over 8 mole HNO3? What's the 1? Is it just, like, why would you just use a standalone 1 for that?
Because it's like I want to divide by 8 moles so I can get the ratio. And to divide it, I do times 1 over something to divide it. It's like if I wanted to divide by 2, I could multiply by 1 over 2. It's the same thing.
Oh, wait, no. I see why you're doing that. It's because you want to plug in the 1 mole HNO3 into that.
Yeah, well, 8 moles of HNO3. And it's because I had, it's like with this cheese sandwich thing over here. I'd had 2 breads, so I needed to take that into account. And I did that by dividing. I had 10 slices, I divided by 2, that gave me 5 cheese sandwiches. So that's how I'm taking into account how much HNO3 I have in the reaction.
Okay.
So
Alright.
we're only looking at like basically the first part of the reaction, and then we're gonna, if we want to, we can compare it to the second part of the reaction. So like say that we wanted to see how much H2O was produced, we would have to say, we would have to compare like one of these ratios to the H2O basically, and see what the limiting reaction is.
Well, actually, there's an easier way of doing that, Roland. Now, in this problem here, this particular problem, we were only interested in figuring out the limiting reagent. The kinds of problems you're talking about, I also go through here in this module, and I'm going to go through one of those examples here. And that's when you want to find out how much of a certain product you get, which is still a limiting reagent problem.
It's just the next step on top of it, basically.
Yes, that's right. Let me see if I can get one of these. Percent yield, no. Okay, it's limiting reagent. Here we go. Okay, so here's an example of what you're talking about. So let's say this is the different reaction now. We've got 4NH3 goes plus 5O2 goes to 4NO plus 6 waters. And here we're given the 2 reactants, which are 10.0 liters of NH3 and 20.0 liters of O2. Now these are at STP, it should say that here, but it doesn't. And what we're interested in here is figuring out the volume of H2O we would get from this reaction. So this is still a limiting reagent problem, but because we're not looking so much for the limiting reagent, we're just looking for how much water we're supposed to get here. So I'm going to go through and do this problem, and we'll see where we end up with it. Now, it's a bit different to what we just did, as I said. And what we would do here, the approach we would take, is we want to figure out how much water we're getting from 10 liters of NH3. And we know we need liters of water because it says volume, and 20.0 liters of O2. So this is a slightly different problem because we need to go one step further than just finding the limiting reagent. It's not like we couldn't find the limiting reagent, we could, but that's not what we're being asked for here. Now we will get it as a consequence though. So we're starting out with 10.0 liters of NH3. We know we need 3 steps to get to liters of H2O. We'll have liters of NH3 on the bottom. We'll have moles of NH3 on the top. We'll have moles of water on the top, and the next part, moles of NH3 on the bottom. And then liters of H2O at the end and moles of H2O at the end. Now the relationship here is going to be 1 mole of NH3, 22.414 liters of NH3. The relationship between moles of water and moles of NH3 is from the reaction, and you see we've got 6 moles of water and 4 moles of NH3. And that leads to 22.414 liters of H2O over 1 mole, and that gives us our answer, which comes out to be, comes out to be 15.0 liters of water. Which makes sense because could have done that in my head, I guess, because you can see that the 22.414s cancel, and it's really just 10 times 6 over 4, which is 10 times 1.5, which is 15.0 liters. And we're starting out with 20.0 liters of O2. And again, we'll have moles of O2 over liters of O2, and then we'll have moles of H2O over moles of O2, and then we'll have liters of H2O over moles of H2O. And again, we plug in our numbers. 1 moles of O2 is 22.414 liters. The relationship between the two is 5 moles of O2 and 6 moles of water, 22.414 liters of H2O, 1 mole. And then our final answer there is 24.0 liters of water. Okay, 24.0 liters of water is how much we get from the O2, and then 15.0 liters of water, that's what we get from the NH3. Now, the thing with limiting reagents is that we know that the limiting reagent here is going to be the NH3, not because we've got less of it, but because it forms less water than what the O2 does. So we know that the maximum amount we could possibly get would be the 15.0 liters of water. We can't get any more of something than whatever we have from the limiting reagent. Limiting reagent is always going to limit the amount of product we get. That's why it's called limiting reagent. So, Roland, that's the other way of doing it, is to figure out how much of a product we're getting, but you have to do a comparison of 2 products.
Yeah. So it's not necessarily because of the fact that 10 liters produces less water versus 20 liters produce, well, 20
That
liters
is the reason. That is the reason.
Oh, so it's the reason. Okay, so
Yeah, but not
so
because there's 10 and 20. That's not the reason.
okay, so like say like would you look at limiting reagent in any way where it's like there's only 4 NH versus 5 O2, so the limiting reagent there would be less because like per 1 reaction it requires less NH No, wait, that wouldn't make sense.
No.
Never mind. I went on a tangent. My bad.
No, you
I
need
just
to,
figured it out.
no, you need to take two things into account always, and those are how many moles you have of something, and also what the mole ratio is at the end. From the reaction. Those are the two things you must take into account. You can't just take into account one thing. It's always going to be two things.
Gotcha.
All right. Any other questions about this? Okay, let's take a look at the assignment here. This assignment is a little bit cruel, I will admit. A lot of people don't like doing it. This is one that people tend to blow off. They say, no, it's too much trouble. I actually think it's really good practice. That's why I have it here. Otherwise, it's not like I'm trying to make people do busy work. I just feel like it's valuable. So let's say we're looking at number one here. This one, we're going from 5.0 moles of H3PO4 to 15 moles of CO2. You're given the reaction in the top here. Note that you also have the conversion in the problem as well, so you don't have to memorize any of that. So let's say we wanted to go from moles of H3PO4 to moles of CO2. Well, we're going from moles to moles, so we need, moles of CO2 will be on top, but it's going to be 3 moles of CO2 from the reaction. That's going to be number one. And then we need, moles of H3PO4. That's 1 mole of H3PO4 is the other one, so that's number 2. And then all these need to have 3 as the unused answer. And that's how you would do these. It becomes a bit more complicated, obviously, once you get down here. Let's say we needed 49.0 grams of H3PO4 and we want to figure out the liters of CO2. So we know it goes, moles of H3PO, 1 mole of H3PO4 will go on top. Now notice this one has a 1 here. That's the first instance of it. So that's one you use first. And then grams of H3PO4 goes on the bottom. That's the molecular weight. So that's number 2. Then it's moles of CO2 from the reaction. And that's going to be 3 moles of CO2. It's going to be number 3. Number 4 is moles of H3PO4 from the reaction. That's 1 mole. That's the second instance. And then we need liters of CO2 and over 1 mole of CO2. And that would be down here. And 1 mole of CO2. Okay, and then everything else gets the unused answer, which is 7. So you can see if you know what you're doing, you can do these relatively quickly. If you don't know what you're doing, it takes some time. But that's the whole point, because I do want people to understand what they're doing. As you can see, it took me 30 seconds to do that, maybe a minute max to do it. It's not too bad. If you know what you're doing, you can get this assignment done in probably 30 to 40 minutes. If you don't know what you're doing, then it's going to be hell and it's going to take hours. Now, I do have videos for every single one of those problems. Every last one of them has a video, so you can, if you're having trouble, you can always go look at the video and see how it's supposed to be set up. Does anybody have any questions? So the percent yield problems are multiple choice, as you can see here. So those are interesting as well. And then you've got limiting reagent ones, which are a bit of a bear, I suppose. Oh dear. All right, it's good practice though. It's all good practice. Does anybody have any questions about the assignment? Remember, if you're having trouble with that, you can always watch the videos. Okay, the practice quiz, once you get to that. And it's the same kind of thing, but you'll type in everything here, including the units and the compounds as you go through it, just like we've been doing. And then you've got your theoretical percent yield problems to fill in the blank here. And the credit quiz looks a lot like that as well. All right, look, I'm really sorry about the problems I was having this morning. They were, it was login related. I don't know what the problem was, but for some reason I couldn't log in. I had to go to another computer and change my password and do all sorts of other things to get in here and get working on what I had to work on. But I don't know what the problem was, but it's been sorted now. Does anybody have any questions about anything that we're doing here? Let me show you what these questions look like on the test as well. So the problems that relate to module 9 start at question 9 here, and we have a problem where you need to go from one thing to another thing, in this case, liters of HCl from grams of Cl2. This is a limiting reagent problem set up very similarly to what you see on the homework. Then percent yield problems, and then more figuring out from where we start to where we finish. What have we got here? No, that's actually module 10. That was it. So it looks like it's 2% yield problems, limiting reagent, and then one of these where you have to go from one thing to another thing. So that's for 9, 10, 11, and 12. And those are the problems that relate to module 9 on the test. So practicing those is always good too, but I would focus on the homework first. I would mainly start with the assignment, and you need to get an early start on it because it does take a while, especially if you're not really confident with stoichiometry. So you want to give yourself enough time to get through that. All right, does anybody have any questions? Anybody have any questions about module 9? All right. Okay. Well,
Could you look at the example, or I guess the page number 7 on the soft chalk? I remember there was a problem there that I found really difficult.
Page 7, you said.
Yes. And then I think it was towards the bottom.
This one here?
Yeah.
Okay. So we're starting out with grams of HNO3. And we're going to liters of steam, which is water. Maybe that was the problem. That
Yeah, that. And I was also just a little bit confused as how to do the conversion and everything.
okay. So we need liters of water at the end. So we know we go moles of HNO3 will be on top here. Grams of HNO3 go on the bottom. Moles of H2O go on the top, and then moles of HNO3 go on the bottom. Liters of H2O go on the top, and then moles of water go on the bottom. And then the relationships, 1 mole, 63.015 grams of HNO3. The relationship between moles of water and moles of HNO3. Go back to the original equation here. 4 to 8, so 4 moles of water, 8 moles of HNO3, then 22.414 liters of water to 1 mole. Now that should give you your answer. And the answer there should be 61.5 liters of water or gas or steam.
So you start off with 1 mole HNO3, then you figure out how many grams 1 mole of HNO3 is, and you divide it by that, the 346, and then you multiply that number by 4 moles of H2O. How'd you figure out that there was 4?
From the reaction, see, 4 moles of water to 8 moles of HNO3.
Okay. So then you multiply the number by 4 divided by 8, which basically cuts it in half again. And then multiply it by, I guess, the moles to liters. Is that the moles to liters conversion right there, 22.4?
Yeah.
Okay. Okay,
Yeah.
that makes sense.
Well, you know, the thing is that when I hear you talking about it, I'd much rather hear you talk about it in terms of going from grams of HNO3 to moles of HNO3 to moles of water and then to liters of water. And then making sure that you understand that all of these are canceling to leave you with liters of water at the end. I mean, that's the whole point.
They're canceling.
Yeah.
How does that work?
Well, the grams of HNO3 have to be grams of HNO3 down here as well. These have to match. So they cancel.
But there's, okay.
Right? Well, it's only the units that cancel, not the numbers, so.
Okay.
And then across the top here is always going to match the flow chart. So grams of HNO3, then moles of HNO3, moles of water, and then liters of water. All of that matches what you see on the top. And then everything on the bottom always matches the previous unit on the top.
22. Okay.
Right? I mean, this is what you have to get used to, David. This is the way you should be doing it. Now, my
This
video
is called stoichiochemistry.
so it's called stoichiometry, but what I'm doing here is called dimensional analysis. It's the way that I also want you to handle stuff like module 3 and module 7 as well, making sure that you're always understanding the units cancel going from the top to the bottom.
Yeah. Okay.
And knowing what you want at the end, and then being able to process the units that way. But always also understanding that anything divided by anything else, anything over something is always equal. So 1 mole of HNO3 is equal to that many grams, 63.015 grams. 4 moles of water is equal to 8 moles of HNO3 from the reaction. And 22.414 liters of water is equal to 1 mole of water. So everything over it's foolproof if you're understanding that part of it.
Okay. Yeah. I think it makes more sense.
Well, you have to practice it though. You have to practice it doing it that way. And
I mean, I was doing dimensional analysis when we were covering significant figures, but it's a little bit more confusing when you get to these conversions.
This is why you have to do it, because you have to make it easier by doing that.
Right.
Otherwise, it just becomes one mess of units and compounds.
Okay. Thanks for covering that.
All right, look at the videos though. The videos I go through, that's exactly how I do the videos for the assignment.
Okay.
So I would definitely look at those and for guidance as well.
Yeah.
Okay. All right. Okay, well, we'll leave it there for today, folks. Thanks for coming. If anybody wants to hang around, ask me questions, they can. Have a good day. I'll see you all Wednesday. Hopefully I'll be in better shape with my logins and everything. I won't be dealing with these technical issues. All right. Thank you. See you all later.
Thank you.
Have a good day.
You too. Jackson, do you need something from me? Nope. Okay.